Welcome, everyone, to another episode of Natural Philosophers, the show in which I talk to some of the leading thinkers of the day about some fascinating topic that they've been working on. I'm your host, Dr. Siddharth Muthukrishnan. My guest today is Professor Sean Carroll. Sean is a research professor of physics at Caltech and an external professor at the Santa Fe Institute. Sean is the author of numerous books, including a standard textbook on general relativity called Spacetime and Geometry, and more accessible books such as The Particle at the End of the Universe, From Eternity to Here, The Big Picture, and most recently, Something Deeply Hidden, Quantum Worlds and the Emergence of Spacetime. He is also the host of the excellent podcast Mindscape, which is an inspiration for my show, for its deep dives into physics and philosophy, among other topics. Sean works on a wide range of topics, including cosmology, quantum field theory, quantum gravity, the foundations of quantum mechanics, the nature of space and time, and philosophy of science. He's an inspiration for people like me who want to straddle the boundary between philosophy and physics. Today, I'll be talking to him about his work on quantum space-time, which is the question of how space-time might emerge from quantum mechanical phenomena. He has co-authored many technical papers on this topic, and a significant part of his recent and excellent book, Something Deeply Hidden, is devoted to this topic in a non-technical way. This is an amazing topic, and it's very interesting to me because it forces us to confront the possibility that the things that seem so familiar and immediate to us, namely space and time, are ultimately grounded in something very alien to our everyday experience, namely quantum mechanics. So welcome, Sean.
Thanks for having me.
So before we get into quantum spacetime, I wanted to ask a couple of questions that are broader. And the first question is the same I ask all my guests, which is, what does the phrase natural philosophy mean to you? Do you think of yourself as a natural philosopher? And perhaps do you think we can identify natural philosophy in today's intellectual landscape?
Well, I'm happy to let people use that phrase. It certainly has a distinguished history, and I don't mind it. I wouldn't, unprompted describe myself that way. It seems like maybe a bit pretentious, but there's no question in my mind that physics or science as it is practiced and philosophy as it is practiced have a great realm of overlap, right? And people say that they're continuous or whatever, but certainly there's no hard right dividing line between them. The organization of the modern university tends to separate them apart, but there's a lot of intellectual commonalities between what they're trying to do, understand how the world works at a fundamental level. So that's why, especially in my field, there's a lot of people who get PhDs in physics and then decide that they should apply for jobs in philosophy departments, because those departments are a little bit more sympathetic to the ways in which they want to try to understand the world. So I don't see any real difference between what we're trying to all do. There's certain different sub-problems we attack, but there's much more common interest between us.
Okay, great. And it seems to me that there's this research spanning physics and philosophy is definitely on the uptick in the past couple of decades. Do you think that's a fair impression? And how do you see the future of this kind of interdisciplinary interaction?
It's hard for me to tell, honestly, because I don't know. I mean, how do you measure that, right? And also, anything that is changing over a timescale of decades is going to be subject to personal selection effects. I was not paying as much attention 5 decades ago to what was going on intellectually as I am now. But with those caveats out of the way, it does seem that way in some ways. And I think it comes from two directions. From the science and physics direction, I'm going to keep saying physics just because I'm way more familiar with physics than biology or chemistry or whatever. But there's a few things going on. One is, there's sort of a good news, bad news situation. The bad news is that fundamental physics has slowed down, right? Progress in our understanding of quantum field theory, particle physics, gravity, things like that. The first half of the 21st century is just a lot slower rate of progress than the first half of the 20th century was. And that's just a fact that I don't think we can get around. the way to make this vivid is to say the last time we were truly surprised by an experimental result in a laboratory in fundamental physics was probably the 1970s. In the 20th century, we were used to being surprised all the time, but our theory caught up with the data and the standard model was put together. And there have been wonderful discoveries in particle physics, but they've all been basically confirming the standard model that was put together in the 70s. In cosmology, we've also had wonderful discoveries, but the only surprising one was the acceleration of the universe, and that was in 1998. That was over 20 years ago, I gotta say. But I think that to a large extent, this is again hard to judge historically, but part of me thinks that this amount of progress that we're seeing right now is just normal. And we were completely spoiled by the first half of the 20th century with relativity and quantum mechanics and the Big Bang and particle physics and radioactivity, all these things in a very short period of time. And the second half of the 20th century, in some sense, was just sort of cleaning up all the mess that was made in the first half. And now we're sort of back to normal again. But anyway, in a situation like that, where progress is hard to make, and also, one can add that the kinds of experiments you need to make progress cost billions of dollars and take decades to build, right? So that's going to slow you down also. In that kind of situation, it's natural to spend at least some of your intellectual effort thinking about the foundations of your field, right? When, if you were in a 1950s particle physicist and you needed to figure out radioactivity and what all these particles were that were being discovered and how to renormalize quantum field theories, you didn't have too much time to worry about the measurement problem in quantum mechanics for the most part. You had stuff to do that was really demanding and right in front of your face. And that's not necessarily the correct attitude, but it's almost an inevitable attitude given how science works. There was low-hanging fruit, people were going to pick it, right? And so I think that there is natural, that's sort of the bad news. Because progress has slowed down on the physics side, it's natural to sort of, we're not done. We haven't figured out all of the answers to the questions we want. So it is natural to sort of go back to the foundations and try to figure out whether or not there is some more deeper question that we can ask that would help us make progress. The good news situation that also drives us in the same direction is that improvements in technology have made certain questions that used to be completely academic now experimentally accessible. And I'm thinking especially in quantum mechanics, quantum computing, quantum information theory, et cetera. So what that means is that our ability to be sanguine about quantum mechanics in particular has become harder and harder to maintain. We really need to understand the foundations of it. It's not just, it's an optional thing and now we have time to do it. We need to do it in order to make progress. What's interesting to me is I think that on the philosophy side, there is a greater acceptance of, bringing what I would call real physics into the fold of philosophy, right? More now than there used to be. There were always philosophers interested in quantum mechanics, but I don't get the feeling that in the 50s, 60s, 70s, 80s, there were a lot of leading philosophers who were, trained as much in the foundations of quantum mechanics as physicists were. So I don't know why that change happened, or even if it did happen, I'm just ignorant of the history of it, but I think that's an important part of it.
Thanks. Yeah, that's really interesting. I myself was in physics and then I switched to philosophy, and I think I can imagine that right now philosophy is much more welcoming to these kinds of transplants than perhaps it had been back in the day. Though again, it's hard to measure these things, and it's hard to see how much of this is just a general expansion of academia as more and more people go to college now, and it's more.
Yeah, it's hard to tell, but for better or for worse, there are now workshops and conferences devoted to the intersections of physics and philosophy in a way that seems more common now than used to be.
Yeah. So one last brief point before we go to quantum spacetime. This is just a point of personal connection between us. So I did my physics PhD at USC, and there I took general relativity with Nick Warner, and I understand that you took general relativity with him in Boston while you were at Harvard. So I just thought that it was kind of funny that it's such a small world that And Nick is a great lecturer, and
I
he
did,
really
yeah. No,
brings it
that was one of
alive.
my favorite courses that I've ever taken, and I had taken a version of general relativity as an undergraduate, but it honestly wasn't that good, and I didn't come out knowing much at all. So when I finally took Nick's course my first year in graduate school, like it all suddenly made sense to me, and I fell in love with it. And a friend of mine, Ted Pine, who's a fellow graduate student, he and I taught general relativity, gave the lectures and everything, our second year in grad school to a fellow grad students in the astronomy department at Harvard. And so that led eventually to a course I taught at MIT, which led to lecture notes, which led to the textbook that I wrote. So Nick was a big influence in all that.
That's awesome that they let you teach your own course at Harvard as a second-year graduate student.
Yeah, I mean, they let you do all sorts of things that are bad for you if, if you ask hard enough.
That's awesome. Okay, so let's turn to the topic at hand, which is quantum spacetime. So if I understand correctly, this research program is inspired, at least in part, from difficulties in reconciling quantum mechanics and gravity. And when we think of this intersection, the two things that come immediately to mind are black holes and cosmology. So can you perhaps more sharply problematize the conflict between GR and QM and
Yeah,
how it relates to
there's
space-time? Sorry.
right. So I mean, I guess should I take just 1 minute to explain both general relativity and quantum mechanics?
Sure. That
General
should be enough.
relativity, yeah, I mean, general relativity is the easy one, as you know, right? Einstein comes along in the early half of the 20th century once again, and he had already figured out, with nudging from Minkowski, his former professor, he figured out that the right way to think about relativity, special relativity, was to marry together space and time into something called four-dimensional space-time. And then thinking about the principle of equivalence, if you were in an elevator, would you know there was a gravitational field, etc. He came up with the idea that space-time should have a geometry of its own. It can be curved, it can be bent, it can be warped, it can be dynamical, changing over time. And you and I feel the effects of that curvature of space-time as gravity. So what Einstein is saying is that gravity is a little bit different than the other forces of nature because it's not living on top of space-time. It's a feature of space-time itself. But otherwise, other than that, slight conceptual shift, it's a pretty straightforward field theory. It's a classical field theory, much like the field theory of electromagnetism and so forth is. So there's both similarities and differences between general relativity and our pre-existing theories of physics. Then there's quantum mechanics that comes along. The first hints are circa 1900 with Max Planck and Einstein also, and then it sort of flowers in the 1920s. And quantum mechanics is an entirely different deal. Quantum mechanics is not yet understood by the physics community. General relativity we understand perfectly, right? I mean, Feynman makes this joke. So there's a series of jokes. Eddington made a joke where soon after relativity came on the scene, a reporter says, I hear that there's only 3 people who understand relativity, you, Einstein, and somebody else. And Eddington hesitates and he says, I'm just trying to think of who the third person is. And then Feynman says, that's entirely BS. Like, as soon as relativity was written down, people understood it. And I think Feynman's point of view here is more accurate. Whereas quantum mechanics, we still don't understand, even though it's 90 years old, right? And the real reason why it's hard to understand is in quantum mechanics, there's a fundamental set of rules that seem to govern the act of observing or measuring something. So quantum mechanics, just like relativity or electromagnetism, has a mathematical setup with, a state of the system that evolves with time, obeying an equation. In electromagnetism, it's Maxwell's equations. In relativity, it's Einstein's equation. In quantum mechanics, it's the Schrödinger equation. But it's the same basic kind of setup, and so far, so good. But the difference in quantum mechanics is that when you measure something, the Schrödinger equation is not sufficient to tell you the answer. You need something extra, and that's the debate about the measurement problem. Does the wave function collapse? All we can do is predict the probability of what the outcome is going to be, and so on. So when you try to, the general thing that we try to do, and this is not what nature does, but this is what human beings do, is to construct quantum mechanical theories by starting with a classical theory, like Maxwell's electromagnetism, and then we quantize it, okay? So we can sort of take the classical theory, apply some rules to it, and get out a quantum mechanical theory. And this is not easy. So for electromagnetism, the theory QED, quantum electrodynamics, which is a theory of electromagnetism of photons, the particles of light, and electrons, the charge carrying particles. It took decades to figure that out. Dirac proposed important steps along the way, and eventually Feynman, Schwinger, Tominaga, Dyson figured out how to do it. Nobel Prizes were scattered all around, and the problem was technical. It was nothing conceptually difficult. It was just that when you tried to plug in the equations, you got infinitely big, crazy wrong answers, and they needed to figure out how to fix them. So we try to do that with general relativity. We say general relativity, okay, space-time is curved, there's some equations, let's plug it in to the formalism of quantum mechanics and see what we get. And you get the same kind of technical problems you got with electromagnetism, but worse. So the technical problems of you get nonsensical infinity answers are still there, but the tricks that Feynman et al. Used to fix them for QED don't work for general relativity. The technical thing we say is we have a non-renormalizable theory, and there's a whole discussion we can have about what that means and whether that's important, et cetera. But the point is that just at the technical level, like let's get some equations that make sense, we've fallen short when it comes to quantum gravity. Our usual toolbox is not up to the task. But then there are also these conceptual problems. So like even forgetting about the fact that if you naively plug in, you don't get the right answer, you should ask, what are you doing? When we were quantizing electromagnetism, we knew what we were doing. We had some fields describing the electromagnetic field, the electron field, et cetera. Those fields had a classical status, and we could quantize them and talk about observables, and the whole bit made sense. With general relativity, we're quantizing space-time itself. So naively, things that you might want to ask, like what is happening at this point in space, right? What would the observational outcome be if I measure something here at this point in space? And in other quantum mechanical theories, you say, well, there's probabilities I will get certain answers. What is the electromagnetic field? What is the quark doing, or whatever? But in quantum gravity, you can't even ask that question. There's no way to specify what you mean by this point in space because space-time itself is quantized. So we're not even sure whether we're doing the right thing in quantum gravity. And forget about the fact that the equations don't work. They might even be the right kinds of equations. Is space-time supposed to be quantized? Is space-time just an emergent phenomenon that is sort of a higher level description hiding something much more fundamental beneath? We don't know the answer to any of those things yet.
To follow up on that, if part of the puzzle is we don't know how to understand what is happening here at this point in space-time, when we're talking about space-time itself, it seems like something like that might arise when we're talking about gravitational waves, right? When we're talking about gravitational waves, we might think, if these are waves in space-time, well, what are they waving with respect to? So, right. But we seem to have moved past that problem.
Well, I think you're right. This is a problem, but it's a much easier problem. But you're right that it's a problem. And in fact, again, I'm going to mention Feynman's name again. There was this argument ever since Einstein came up with general relativity. So Einstein says that space and time are curved, that's gravity, etc. He also manages to build in the restrictions of relativity into the theory of gravity. So in Isaac Newton's theory of gravity, it's very simple. There's a force between two objects. It fades off as 1 over the distance squared, the famous inverse square law. But there's also no speed of light limitation in Newtonian mechanics. So you move something here, it instantly affects the gravitational field far away. In general relativity, that's not true. You move something here and the signal propagates outward at the speed of light. So therefore, you naturally expect that if I have a heavy object here and I move it, like if there are two objects orbiting each other, there should be waves traveling out at the speed of light. That's the natural thing to expect. And indeed, Einstein first guessed that. But as you sort of allude to, things are subtle in general relativity. And if space-time itself is the thing that is vibrating, can we maybe just find a set of coordinates in which what we thought was disturbance in the gravitational field actually isn't there at all? And the answer to that question is sometimes you can, and sometimes you can't. And so there were, there's all sorts of, events in the history of general relativity where people thought they had found an important new phenomenon, and someone else realized it was just a new coordinate system for an old phenomenon that we already understood. So Feynman went to this conference in I think it was the 1950s or maybe the 60s, about gravity. And people were arguing over whether gravitational waves were real. Okay, this is like 40 or 50 years after general relativity exists. And so he argued that he could show that if you had a stick, right? I don't have a stick right here. Oh, here's a stick. So if you have a stick and you have a ring, I do have a ring. Okay, so I'm going to do a demonstration here on the video. He says that he could show that if you held the stick, a gravitational wave would make the ring move back and forth. And therefore, it would heat up the stick. And therefore, energy would be transferred. And therefore, the gravitational waves must be real. Okay, this is the level of discourse that we had 40 or 50 years after general relativity. So the subtlety there was, it's hard to pinpoint things in general relativity. The short version is, at any one point in space, you can make it look just like you're in flat space-time and nothing is going on. But as soon as you consider a region of space, which is even a really tiny region, then the curvature of space-time becomes important. So the questions are important with gravitational waves, but they are answerable, and the gravitational waves are really real. In quantum gravity, here's the problem. Quantum mechanics of ordinary point particles, like an electron, right? We say that the electron is described by a wave function, some kind of cloud of probability that gives us the probability. If you take the wave function, you square it, you get the probability you'll observe the electron at different points. So we think of that as saying the electron is in a superposition of existing at all these different points in space. There's like a little bit of it that exists at all these different points. So if you just would do the straightforward quantum recipe and apply it to gravity, what you're saying is that space-time should be in a superposition of having all different geometries, right? It's flat, it's a little bit curved, it's a lot curved, etc. So, okay, you could describe that mathematically, but what you can't do is say, so if I have a point in one of the geometries that I'm superimposing, and I have another point in a different geometry that I'm superimposing, are they the same point or are they different points? There's literally no answer to that question. It's not that you have to be clever to figure it out. It's an unanswerable question. There's no simple, straightforward, agreed upon, natural, universal way of comparing these two space-times. But they're both part of the quantum state of the universe. So what are we doing? And so again, it might be that these are answerable questions, but well, there might be answerable questions. There might be the correct questions to ask, but the ones that we're used to asking are not those.
That's great. So
I apologize if my answers here are too long. I'm just very enthusiastic about these.
Oh no, these answers are absolutely fantastic and very helpful. Thank you. So you, to go back to your point about quantization, where you said that you take classical field theories and then you try to quantize them. So is it fair to say that the most popular approach to quantum gravity, namely string theory, is one such approach?
Yeah, string theory is, so let me back up a little bit to go back to this distinction between technical problems and conceptual problems, right? String theory is a theory of quantum gravity which grew out of particle physics. It didn't come from gravitational physicists trying to quantize gravity. In fact, string theory was invented in the 60s and 70s by people who are trying to understand the strong nuclear force, okay, why quarks are bound into protons and neutrons. And they kept running across the problem. I mean, the basic idea is you say, well, instead of a little point particle, let me hypothesize that the fundamental constituents of matter are little loops of string or little line segments of string, okay? And again, we have rules for taking theories and quantizing them, right? So you say, well, I can write down a set of equations of motion for a little loop of string, a relativistic loop of string, and I quantize it. And things happen, you get certain kinds of excitations, just like, you get certain modes or certain, just like an atom gives off certain spectral lines, there are certain vibrational modes of a string. And what they kept finding over and over again is that some of those vibrational modes looked like gravitons looked like they were the force-carrying particles of gravity. And the first reaction was, well, we don't want that. We've clearly made a mistake somewhere. And eventually, people, including my Caltech colleague, John Schwartz, said, well, look, gravity exists. Maybe this is actually a feature rather than a bug. Maybe we have a quantum theory of gravity here. And what they were able to show is that it's a consistent theory. It's finite. All these infinities you were worried about just go away in string theory. So without even trying, this is why string theory was so compelling. Without even wanting to, without even meaning to, you invented a theory of quantum gravity where all the technical problems seem to be solved, right? So of course people are going to be just ecstatic about that and very, very interested in it. The conceptual problems of quantum gravity weren't solved at all by string theory. Like they just sort of did the straightforward, follow your nose kind of thing. Now, to be fair, the amount of intellectual firepower that has been devoted to string theory over the past few decades is amazing. Some of the smartest people in the world devoting their lives to this, and they've made enormous progress and had enormous discoveries at the theoretical level. There's zero experimental evidence that they're on the right track so far, but conceptually and theoretically they discovered amazing things, such as the holographic principle, the principle of complementarity, the duality between different theories that live in different numbers of space-time dimensions. And we can go into all of these in detail if you want. But the point is that even though string theory did not start out trying to solve conceptual problems of quantum gravity, it has nevertheless made progress in teaching us conceptual things about quantum gravity. But I think that original lack of interest in the conceptual problems still lingers. Still most string theorists are kind of down to earth about their approach. They don't become philosophers, right? They want to solve the equations. They want to calculate amplitudes and get probabilities and things like that. And that's led to immense progress. But I think, there's still these lurking questions in the background that haven't been addressed.
So would it be fair to say that with quantization approaches like string theory, it's perhaps easier to get space-time because you're quantizing whatever it is that should represent space-time. But then the rest of our physics, all the other quantum field theories that describe ordinary matter, that getting that right is harder. Whereas perhaps with the quantum space-time approach, which we should talk about more, that one is trying to perhaps solve both these problems in one go.
Well, I think it's a tricky situation even just within string theory. Like the original string theory, old school string theory, like pre-1995, 96, okay? They didn't get space-time. They just put space-time in by hand. When they wrote down the theory, they said, here's space-time, there's a string moving in space-time, we're going to quantize that string, okay? And what they found were, and it was really, again, it was remarkable, and if you go through the math, it's hard not to be charmed. What they realized was there's certain constraints on when the theory can be technically okay, when you can get rid of these infinities and so forth, when you have a well-defined theory, and those constraints included restrictions on what geometries you could have of the space-time through which the strings were moving. And what they showed is that the geometry of space-time has to obey Einstein's equation of classical general relativity. So that's how you get classical general relativity out of string theory. But you never get space-time out of string theory. You put that in by hand. Now, I say that's old school string theory pre-1996 because there was what we call the first superstring revolution in 1984, where they finally proved that everything was finite and well-behaved. But still, old school scattering particles or strings off of each other. Circa the mid-90s, the second superstring revolution happened here, and that's where holography and duality and all these other concepts became to the fore. And there, one thing that you absolutely have to mention is what is called the ADS Cft Correspondence. And this was put forward by Juan Maldacena, I think in 1996 was the year. And what he realized is that it had been known for a long time that in quantum mechanics, two very different classical theories could actually give you the same quantum mechanical theory. And that's what a duality is, right? Like one quantum mechanical theory can look classical in two very, very different ways. And so what Maldacena showed is that there's a duality where you have one theory that is just an ordinary quantum field theory in flat space-time. No gravity, okay? Just particle physics as we know and love it. Forget about all the details of quantum gravity, okay? In 4 dimensions. And then there's another theory that is string theory, quantum gravity, in 5 dimensions. And these two theories are secretly the same. There's a duality between them. And like the world was like, this is amazing. Like how in the world is this happening? And in that sense, if you believe that, and people will, will argue over the rigor with which this is established, because to be fair, we understand the quantum field theory flat space-time side of the duality much better than we understand the quantum gravity side. Surprise, surprise. So the quantum field theory flat space-time bit is perfectly well defined. We know what's going on there. We're claiming it's the same as the quantum gravity theory, but maybe the quantum gravity theory is just an approximation to the other theory. Since the quantum gravity theory is not by itself well defined and rigorous, it's hard to say it's exactly the same theory. But anyway, in that context, there's a very real sense in which one kind of space-time is emerging out of a different kind of space-time, right? A 5-dimensional curved space-time is emerging out of a 4-dimensional flat space-time. So it's not that space-time is emergent, but at least a kind of space-time is emergent, and what's emerged from is a different space-time. And so, that you got to give him credit for that. That is an amazing, important fact that any other competitor theory of quantum gravity is going to have to do at least as well in questions like that.
Yeah, so just to quickly follow up on that, and I've heard that kind of locution a lot even when people talk about string theory and ADS-CFT, that one kind of space-time comes from another kind of space-time, and perhaps, am I right, like the terminology, something like target and background or something like that. Is that the right?
That's a different terminology.
Oh, sorry, I don't mean to confuse the waters. Okay.
No, I mean, this is very interesting. So again, this is sort of old school string theory. Here's an issue that you have. You say, well, I have space-time and here's a string moving through space-time, okay? Well, what does that mean? It means that I have, mathematically, there's a map from, let's say, a cylinder, which is like the world sheet of a string, into space-time, okay? But equally well, I could take space-time as a field living on the string. So at every location on the string's world sheet, there are different fields telling me where I am in space-time and what the quantum fields in that space-time are, okay? So in other words, I can treat space-time as where things live and the string is moving through it, or I can take what we call this world sheet point of view and take a single string as what the universe is, and all the fields of space-time are defined on that string. Okay, so this is a target space versus a world sheet kind of point of view. And that's just old school string theory. The ADS-CFT stuff is, sounds similar because there's maps between spaces, but it's a little bit different.
Right. And can someone perhaps say in these kinds of discussions that one of them is not really space-time, even though it has the same mathematical structure, and the other thing is really what we are acquainted with as space-time?
Well, that sounds like a deep philosophical question. Let's just take ADS-CFT. So ADS, by the way, ADS stands for anti-de Sitter space, meaning a cosmological space-time with a negative energy in empty space. That's the gravitational background that Maldacena was talking about for his duality. CFT stands for conformal field theory, which is just the flat space-time field theory that he defined. That's why it's called ADS-CFT. So they're both space-times, both sides of this duality. They have different numbers of dimensions in them, right? But they're both space-times. And so there's two really subtle, difficult questions that arise, which, to be honest, the string theorists haven't worried about that much, because, they are down to earth, nose to the grindstone folks. And the two questions are, number one, if that were the correct theory of the world, right? It's not, because In the real world, the vacuum energy, the energy in empty space, is a positive number, not a negative number. So we don't live in the ADS-CFT toy model universe. But if we did, what would we think space-time was? Would we think it was anti-de Sitter space, or would we think it was flat space-time, right? And I think the answer is it depends. I don't think that there's a simple answer there. But to be honest, this has not been fully worked out. I've not seen, an exact answer to that question. From the point of view of the theory, they're both space-time. Like, there's no preference for one over the other. So the question of what you see when you live there is way harder than it sounds. It involves things like the classical limit, which involves things like decoherence and foundations of quantum mechanics and other, why is there a classical world at all? Okay. Which things that I'm personally extremely interested in, but are not the things that string theorists spend their professional lives worried about. The other question is, like I said, we don't live in ADS-CFT. We don't live in a negatively curved spacetime or a flat spacetime. We live in a positively curved spacetime. So what are the implications of ADS-CFT for the real world, right? Now, that is something that string theorists have worried about. People have tried to come up with other versions of the correspondence or other implications, but nothing is anywhere near as compelling as the original ADS-CFT. We do not have a theory. I think it's safe to say we don't have any kind of theory that anyone would propose to think about our four-dimensional world with gravity as equivalent to a straightforwardly defined three-dimensional world without gravity, right? That might be what you want, but nature is not giving that to us in any very simple way. And that's okay. It's a hard problem. That's all right. No one ever promised us a rose garden. But I do think that, if I want to be a little critical of string theory, there's just an enormous amount of effort that goes into understanding ADS-CFT. The joke that I tell is, or the joke that I repurpose, is the old drunk guy looking for his keys, right? The drunk guy lost his keys. You see him, he's looking under a lamppost for his keys. You ask him for if he needs help, and then you don't find them, and you say, like, well, we don't see these keys anywhere. Are you sure you dropped them here? And the drunk guy says, oh no, I dropped them over there, but the light is much better over here, right? So ADS-CFT is the world's most powerful lamppost if you're a theoretical physicist. It's not where we live, but it's where we can look. So people spend a lot of time thinking about that. And hopefully that thought will lead to greater wisdom and insight, which we will eventually apply to the real world. But a whole generation of string theorists has come up and matured without any attempt to connect to the real world at all. And that can be problematic for different reasons. Right.
Okay, so let's turn to the quantum spacetime approach itself, which you're fond of, at least somewhat. So I guess to some people, it might be surprising, the idea that spacetime emerges from something else. And it seems to me that other approaches actually don't really take that point of view, right? Because they have some kind of space-time already in place, which allows them to get further features of our space-time, or things that look like our space-time. So I think we need to get into a little bit about Hilbert spaces and wave functions on Hilbert space, and how something like space-time can come out of that kind of structure. So perhaps you can take it away and give us a brief overview of that.
Yeah, it's a long journey, so buckle up a little bit. And look, let's again just be, I want to not only say what I think, but I want to give an impression of what other people think at the same time, because shockingly, not everyone agrees with me about these important issues yet. So when we do quantum mechanics, we already mentioned that you can start with an electron, which classically you would describe as having a position, there it is, and having a velocity. And Isaac Newton says, from that, you can predict what's going to happen to the electron. And quantum mechanics says, no, there's no such thing as the position and the velocity. What there is a wave function, which says at every point that the electron could be at, there's a complex number, and you square that number to get the probability that you would observe the electron there were you to look at it, okay? And you can do the same thing for the momentum, but it's a separate process. And so already, like even at this very basic first step of quantum mechanics, we're at a hugely controversial issue that we don't agree about. Namely, is that wave function real? Is the world really some kind of wave function, or is the wave function just a tool that we're using to make predictions for experimental outcomes? Or is the wave function real, but something else is also real? Okay, like none of these very basic elementary questions are things that we agree on yet, which is very embarrassing, okay? So any question about, you know, what is the fundamental nature of this quantum theory that you're thinking about will be different depending on your attitude toward that kind of foundational question. My attitude is, of course the wave function's real. Like every version of quantum mechanics has wave functions in it. Some versions have other stuff. Some versions don't say it's real, but they all have wave functions in it. Let's at least start with the simplest possibility that the reason why the wave function is so important is because it's real, because it really describes things. But it quickly gets further and further away from our everyday experience, because you think of the wave function for one electron as living in space. Like at every point in space, there's a value, okay? And you just calculate that value, it tells you the probability, et cetera. Like that's something we're familiar with. That's just a classical kind of field. At every point in space, there's a value for the field. But no, let's say you have two electrons. I mean, in the real world, you have lots of electrons, so two does not seem too dramatic. And one of the very many miracles of quantum mechanics is that if you have two electrons, you don't have two wave functions. You have one wave function, and the one wave function, rather than being a function of where electron 1 is, it's a function of both where electron 2 is and where electron 1 is. So if you think that there's a three-dimensional space of where electron 1 could be, and a three-dimensional space of where electron 2 could be, the same space, like, you know, the different locations for electron 1 and electron 2, then the wave function is a function on a six-dimensional space, not on this three-dimensional space we live in, but the six-dimensional space. And if you have 10 to the 26 particles, then the wave function is a function on a 3 times 10 to the 26 dimensional space, okay? So this is already a very abstract mathematical kind of thing. Happily, there exist mathematicians who are willing to formalize this for us. David Hilbert, one of the greatest mathematicians of the 20th century, described how you can treat things like quantum mechanical wave functions as vectors in a giant dimensional vector space. So, you know, we're used to three-dimensional vectors. Hilbert is saying that actually you can imagine infinite dimensional vector spaces. Even a single electron, even if its wave function, is described by an infinite dimensional vector space, because the dimensions of vector, and this is more than you need to know, but I can't resist saying it anyway, every position that the electron could be seen in defines a dimension in the vector space that we call Hilbert space, the space of all possible wave functions. And so here is an attitude you could take, not necessarily the only attitude, but an attitude you could take is, look, all of this talk about positions, that's just old-fashioned baggage from our classical, you know, intuition and education that we grew up with. You know, we see things in the world, so we think that things have the property of having locations in the world. But we should face up to the reality of quantum mechanics, right? And what quantum mechanics is saying is that the world is not a bunch of objects living with locations in space. The world is a vector in a Hilbert space, this humongous vector space. It might be infinite dimensional, or it might be just finite dimensional, but really, 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 really big dimensional, okay? And again, that vector doesn't know or care that we like to think of it as a function in some big space. It's just a vector. It's a vector in a big Hilbert space. And mathematically, formally, that's all you need to describe quantum mechanics. You don't need to use words like space and location. You have a vector, it's in Hilbert space, it evolves according to the Schrodinger equation, you're happy and you're done. And so there is I forget whether I'm actually answering your question or not, but let me at least prefigure where we're gonna go. There is an attitude you could take toward quantum gravity, fundamental physics, emergent space-time, which says, you know, maybe we've been held back by the idea that we start with a classical theory and then quantizing it. right? Nature doesn't do that. Nature doesn't start with a classical theory and then quantizing it. In fact, one of the lessons from these dualities, like ADS-CFT, but also pre-existing much more down-to-earth dualities, is two different classical theories can give you the same quantum mechanical theory. Or thought of another way, the same quantum mechanical theory can have two very different classical approximations, right? So we shouldn't privilege this connection between some pre-existing classical theory and the quantum theory. The world is quantum. What we should do is write down quantum theories, theories of vectors in Hilbert space, and then do the hard work of trying to understand why they look like the real world, right? Like why they look like objects living in three-dimensional space. And so that is the attitude that I would like to take. It is enormously primitive and just at the beginning stages compared to something like string theory or other approaches to quantum gravity. So it might crash and burn and be a complete failure, but I think that, you know, conceptually, it's something we got to try.
Yeah, so the thought is that at the very fundamental level, or at least at a level that's more fundamental than space-time and gravity, what you have is a quantum mechanical wave function living in a infinitely large or perhaps ginormously large Hilbert space, and the behavior or the properties of this wave function lead to what looks like to us to be something like a three-dimensional space, a one-dimensional time, matter on these quantum fields living on the space and time. And our familiar physics is really some kind of shorter description, or perhaps more, if something that looks to us at a classical level or at a higher level to be what it is, whereas in reality it's very, very high dimensional wave function doing
That's
what
right.
it does.
The classical description, or even let's use the word semi-classical, because the world that we observe is mostly classical, right? But there are, you know, nuclei decay, there are radioactive events, there are quantum jumps of electrons from one place to another. So the world that we live in is like 99% classical plus a little bit of quantum fluctuation jumping, and that describes the world very, very, very well, okay? So the idea would be that kind of description, semi-classical, mostly classical plus some quantum jumps, emerges as an approximation in the right circumstances to some deeper, fully quantum reality, okay? And in a very parallel way to how we talk about air in the room as a fluid with a temperature and a density and a pressure and a velocity, even though we know it's really made out of atoms and molecules, okay? That's not a perfect analogy, because that analogy makes you think that emergence as a concept is fundamentally tied to little itty bits that come together to make bigger bits. Whereas this quantum to classical emergence is something much more conceptual, and, you know, it's not like there's little quantum dots. Like, one of the misconceptions about quantum theory is that it sort of divides the world into microscopic pixels and everything smoothly emerges from that. That's not it. That's not how quantum mechanics works at all. It's much more complicated and subtle and nuanced than that. But conceptually, yes, the idea would be that the quantum language, the quantum description of the world, sounds very different than our classical language. So the work to be done is to understand why classical physics is so good, how the classical world emerges. And, you know, if you take this attitude that I said, that, you know, reality is the quantum wave function, the vector in Hilbert space. By the way, this attitude sometimes goes under the name of the many worlds interpretation of quantum mechanics. And we haven't mentioned that yet, but many worlds is disreputable in certain circles because of all those worlds. But the fundamental posit is just that the wave function is real and it always obeys the Schrodinger equation. And so that work to be done of saying, well, there's a vector moving in Hilbert space, let's connect it to the real world, you know, that should have been started as a serious high priority, high prestige research program in the 1950s. But it wasn't, and still isn't. And so there's some, you know, it's great fun because there is so much low-hanging fruit. Like there's so basic questions that we haven't yet answered in this world, because we always cheat when we do quantum mechanics. We always know the answer, what the classical world is supposed to be, ahead of time. So we start with that and we bake it in to how we do quantum mechanics. So this very fundamental challenge of how would you extract the classical world from a quantum system if you didn't know ahead of time what it was, is still sort of a cutting edge research topic.
Yeah, I mean, another way that I think about it is that it's kind of surprising to me how successful the quantization approach really has been in a way, because if once someone learns something about quantum mechanics and starts thinking about how classical physics approaches, turns out that that story is actually very complicated, right? And typically you have to
Yes.
you have to do things like decoherence and decompose things into systems and environments, and figuring out how the system behaves in the limit of these interactions is actually quite complicated, and many physicists spend their whole lives thinking about these things. So it's kind of surprising to me that what if we think of the quantization approach as taking a classical limit and then guessing that the quantum mechanical form is going to be very similar to the classical form. That is, the equations have very similar formal structure.
Yeah.
It's kind of surprising that we kind of lucked out in a way. The world needn't have been like this. It could have been that the quantum mechanical structure is much more inaccessible from the classical physics, right?
Well, yeah, and this is why you're revealing why you're philosophically inclined, because exactly this is a really interesting question. Why is it like that, and why is it like that both ways? You just said, the quantum mechanical structure could be much more hidden, but the other possibility is that the classical structure could not be there at all, right? Like there's no guarantee that a quantum theory has a classical limit in any sense. So why are the laws of physics taking the form that they need to give us a classical world at all? And it's probably not just the laws of physics. There's probably also questions of initial conditions, right? The certain quantum states can be described as approximately classical and certain ones can't. So why do we live in a universe that allows us to describe it that way? These are great fundamental questions that people don't really address. By the way, I will, just between you and me, don't tell anybody, but now that I've written Something Deeply Hidden, I kind of secretly look forward to like the next 5, 10, 20 years when there's a bunch of people who read that book in high school and then go and take quantum mechanics in college and ask their professors a bunch of really uncomfortable questions that they were not used to receiving in previous years. Because, quantum mechanics, when you're taught it as an undergrad, it's just magic, and you're just taught to, shut up and calculate. And I hope that I've ruined that experience for future generations of quantum mechanics instructors.
So just to be clear, when you said between us, you would like me to edit that bit out, right? Is that?
No, I'm just kidding. You can
Oh,
let
you're
everyone
just
else know.
I just want to make sure. Okay, so right, yeah, I completely agree that it's not helpful to teach quantum mechanics as magic. And when I learned it as an undergraduate, I was completely confused, and it took me only in graduate school did I even start beginning to understand it really. Maybe that's not fully true, but okay. So good. So we have space-time as some kind of classic, not some kind of semi-classical limit to some kind of quantum mechanical wave function, and it's I briefly mentioned decoherence, and perhaps how maybe you can briefly tell us what decoherence is and why that might be an important part of the story.
Sure. I mean, it's a critically important part of the story, and one that is not always appreciated. Like many introductory quantum mechanics books, you will not find the word decoherence in the index. And this is one of the reasons why I'm writing an introductory quantum mechanics book to remedy this situation. I think that you can't understand quantum mechanics in the real world without understanding decoherence. So what is it? I actually like to introduce this via Schrodinger's cat. Right? The classic example, you have a cat in a box, you hook up some elaborate quantum mechanical system that puts the cat, by the straightforward, naive rules of quantum mechanics, the cat is in a superposition of awake and asleep. The classical version is that he's in a superposition of alive and dead, but I see no reason to kill the cat. So in my book, I make sleeping gas be in the box. And so Schrödinger, who came up with this, his point of the Schrödinger cat experiment was, surely you don't believe this. Surely you don't believe that in a box, until I open it, the cat is both awake and asleep, right? And then when I open it, it suddenly pops into one or the other. And, people debated back and forth, but the decoherence story is simply arises from the thing that we already said, which is that what we said was when you have two electrons, you don't have a wave function for electron 1 and a wave function for electron 2. You have one wave function for both electrons. And that principle generalizes. That's true for the whole world. This is one of the features of quantum mechanics is there are not separate wave functions for different subsystems of the universe. There's just one wave function for the entire universe. And that's what allows for entanglement between different systems. So you can have quantum systems where you don't know what you will observe with subsystem 1 or with subsystem 2, but if they're entangled, then when you observe subsystem 1, you instantly learn something about subsystem 2, even though it's very far away. So this is what Einstein worried about under the phrase spooky action at a distance. But it's there, it's part of quantum mechanics. So really, when you do quantum mechanics honestly, you should always keep in mind that you can't separate out one little quantum system from the rest of the world. If they're interacting with each other, then they can become entangled. If you're just doing particle physics, if you're smashing two protons together with the Large Hadron Collider and looking at the little tracks they leave in your detector, then whatever, you just treat the two particles. You don't need to treat the rest of the world because they're not interacting until they actually hit the detector. But if you have a cat in a box, then of course it's interacting with everything else in the box. So there's light presumably in the box, but there's certainly air molecules in the box. So we group together all that other stuff, all the stuff in the box that we're not keeping track of explicitly, and we call that the environment. And the question is, there is an important non-trivial quantitative question here. Does the environment become entangled with the quantum system that you care about? In the case of a cat, if it's in a superposition of being awake and running around the box and being asleep and laying on the floor, then of course the environment interacts differently with the cat in those two states, right? A certain molecule might hit the cat if it's awake, and if it's asleep, it'll just miss the cat. So instantly there's entanglement. That's what you need to get entanglement. You need not just an interaction, but an interaction that behaves differently depending on the different parts of the superposition that you're in. So the point is that if you consider just the cat, you're allowed to consider just the cat. You're just not allowed to think that it's isolated, okay? It's interacting with its environment and becomes entangled. So the cat doesn't have a wave function all by itself. If you ignore the environment, then you don't know what the wave function of the cat is. It's in a mixture of being awake and being asleep. It's not in a superposition. A superposition is an isolated thing that, there's a state of the cat that is unentangled with the rest of the world. But once it becomes entangled, then the state of the cat corresponding to awake is completely separated now from the state of the cat that is corresponding to asleep, because they have interacted with the world in a different way. And that phenomenon of interacting with the world in a different way and becoming entangled is called decoherence. So really, what a many worlds person, what we call ourselves Everettians, after Hugh Everett, who proposed many worlds interpretation back in the 1950s, what an Everettian would say is, when the cat became entangled with the environment differentially, when the awake part of the cat interacted with the environment in some way, and the asleep part interacted in a different way, that was the moment of decoherence. And at that moment, the wave function of the universe branched into two different worlds. There's a world in which the cat was awake and a world in which the cat was asleep. And, Everett said this because Everett was a genius, but honestly, I don't really think he had a right to say that, because he didn't know about decoherence. He didn't talk about the environment. He had some other arguments that were very clever, but I think that decoherence, by which we mean becoming entangled with the environment, is absolutely crucial for claiming that the awake cat and the asleep cat are truly living in two different worlds. And the reason why is because those environments are different. If you imagine counterfactually, if we put on our philosopher's hat now, right, and we think about causality, and you say, well, I don't know exactly understand what causality is, but it has something to do with the fact that if I did this, things would happen. If I didn't do that, that wouldn't happen. So if you do something to the awake cat, whatever it is, you can show mathematically that once decoherence happens, the asleep cat is completely unaffected. There's no causal influence of what happens in one branch of the wave function to what happens in the other branch of the wave function. That's why it's okay to think of them as separate worlds. There's no quantum mechanical interference, or there's no direct interaction between anything going on. If you move a planet in the world, you know, if the alive cat, the awake cat, you know, bats a toy, okay, and the toy is electrically charged, so it has an electric field. So it has a little electric field and it bats the toy, or maybe a magnet or something like that. In the world where the cat is asleep, the electric field does not change, okay? So the worlds are truly different, truly distinct in that sense. And that's because of this decoherence phenomenon. And so I do think that the way we teach quantum mechanics, not only do we ignore conceptual issues and foundational issues like the measurement problem and ontology and reality, but even down to earth, critically central, calculational technical issues like decoherence are ignored in conventional treatments. And I think that we need to do better.
Yeah, I think decoherence is, of course, essential to explain the emergence of classical reality. And it's kind of interesting you mentioned that Everett did not know about decoherence. And yeah, it's kind of surprising he came up with his theory without it. And I think I'm right in saying that Hans-Dieter Zeh, who was one of the founders of decoherence, took that to be a vindication of Everett's ideas and a sharpening of them. And he was fairly explicit as an Everettian, if I remember correctly.
I think so, but I'm not gonna swear that I'm on the right track there with Zeh. But you know, he does. Hans-Dieter Zeh deserves an enormous amount of credit. He and Zurek and some other people who really in the 70s and 80s pioneered decoherence as a crucial thing. And by the way, just for the listeners or viewers who are not embroiled in the current state of quantum mechanics, I'm presenting decoherence here as something that is central to Everettian quantum mechanics and the foundations of quantum mechanics and the emergence of classical reality. But decoherence is also really important for people who are building quantum computers, right? Like, it's not something you only need to worry about if you're philosophically inclined. You need to worry about it if you ever want to maintain a quantum system in a superposition of two different possibilities without the external world interfering with it and becoming entangled with it and decohering. So the whole challenge of building quantum computers, the whole technological challenge, is avoiding decoherence.
So to go back to the question of how space-time might be emergent due to decoherence, I imagine the idea is that earlier you mentioned we could have superpositions of different geometries. And the thought is that these different geometries count as worlds that are stable and can support their own dynamics precisely because of a kind of decoherence. Am I on the right track with that?
I mean, I think I got to say, we would like that to be true. We like something like that to be true. It turns out to be a really tricky problem. I think this is one of the very easy questions to ask and hard to answer. In the case of Schrodinger's cat, there was a very clear and pretty agreeable differentiation between the system, the cat, and the environment, like all the air molecules or whatever, okay? What is the corresponding thing when it comes to space-time? What is the system and what is the environment, right? Like, what are we entangling with and what is being entangled? I don't know. I'm not sure. Like, my most recent paper is about exactly like the first really tentative baby steps toward being able to answer questions like that. I wouldn't be surprised if there isn't some simple, robust answer that we can all agree on, but I don't know what it is yet. So certainly what I expect to be true is that under the right circumstances, which include the circumstances we live in the real world, there is a sensible factorization, we would say, into macroscopic systems and environments that we can sort of ignore the details of. And they branch the wave function of the universe into different worlds with different semi-classical geometries that obey Einstein's equations of general relativity to a very high precision. If we don't get that, then we have not gotten a very empirically effective rule of quantum gravity.
Yeah, I guess one subtle point with this separation of system and environment is that people might intuitively think that a system is some spatial region and the environment is the rest of the world. But actually, it's more general than that. And even in the case of Schrodinger's cat, you can imagine that the degrees of freedom inside the cat, such as the magnetic field of the nuclei of the atoms or something like that, that don't matter to whether we count the cat as dead or alive, might also be in a way an environment because we don't keep track of them or we don't consider it as part of the system that we care about, right?
Yeah, no, that's absolutely true. And in fact, it's a reason why I think that one of my interests at the research level is just a better understanding of emergence more generally, because you're absolutely right that let's do a simpler example than a cat. Let's do the Earth orbiting the sun, okay? This is my favorite example of emergence. When we do the Earth orbiting the sun, I don't need to tell you where every molecule in the Earth is, right? I don't even need to tell you like where the oceans are and where the continents are. I just give you the center of mass of the Earth, its location and its velocity, and I can figure out how it moves around the sun. All of those, what we call internal degrees of freedom, the individual locations of atoms and different things going on in the Earth, are irrelevant to the question of how the Earth orbits the sun, to a very, very, very good approximation. Not perfect, but very, very good. So yeah, I could absolutely quantum mechanically describe the Earth very simply as a point in a three-dimensional space. And all the other things, all the internal jigglings of the atoms are part of the environment. What we would like is a recipe, an algorithm for doing that in general. Like we can do it on a case-by-case basis and it's fine, but we don't have this general algorithm for doing it. And the reason why we can do it on a case-by-case basis is because decoherence is really, really, really effective. You know, the time scale over which things decohere are like shorter than the lifespan of a Higgs boson that we make at the Large Hadron Collider, right? Like just a few photons bumping into you are enough to decohere you. And there are many, 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 many photons bumping into you every second.
Right. Okay, so to go back to space and time, so if space-time is to emerge from quantum mechanics by some such recipe, then presumably the space-time that we get out has to satisfy several constraints, right? So our space-time as we know it has a certain dimension. We assume that it has a certain topology. We assume that it has a certain geometry with a certain mathematical structure, which gets called pseudo-Riemannian to be fancy. It has certain symmetry properties. It satisfies Einstein's equation. There's a lot of detail in the structure of space-time as we know it. And it seems to me like quite hard, to say the least, to imagine getting all that structure out of something extremely austere as a wave function on a very large dimensional Hilbert space.
Yes. It does indeed seem very hard. This is why we're paid such big bucks for doing it, right? Because the challenges are so noble and daunting. Yeah, so look, there's so many things to say that I'm not sure where to start. But one thing, the positive case is the following. Sure, it does sound hard to start with just saying, well, we have a vector in a Hilbert space. We also have what is called the Hamiltonian. Okay, the Hamiltonian is the quantum mechanical way to figure out how much energy there is in different parts of the wave function. And the Schrodinger equation basically says that the Hamiltonian, when applied to the wave function, tells you how it evolves. It tells you how it changes over time. And so we actually have not just that there is a vector in Hilbert space, but we have two other things. We have the Hamiltonian that evolves it, and we have what particular state we have, right? There's some initial condition or something like that. So those are the ingredients we're allowed to use. And we want to ask, well, okay, out of that, get the world, get space-time, get geometry, get all the standard model particle physics, all the fields and all that stuff, okay? It sounds extremely daunting, and that sounds bad. But on the other hand, given that we know that what we need to get is space-time and the standard model and so forth, if quantum mechanics as we understand it is right, there is some Hilbert space and some Hamiltonian that gets us that. So it's reverse engineering is the problem, right? Like, how do we go backwards? If we know that we have to be able to go forwards, then presumably we should be able to go backwards. And that's why we're just sort of beginning to nibble at the easy problem of the general question: how do we go from a quantum mechanical vector in Hilbert space to some physical system? And we're learning a lot along the way about doing that, and it's hard. But that's sort of the positive case. Like, the positive case is it had better work. If, if physics works how we think it is, how we think it does, it had better be possible to do something like this, even if it's really hard. There's a lingering question, though, which is that when you put things in that language, there's just a Hamiltonian, it's acting on the wave function, etc. Is there a reason why something like our world comes out of it at all? Like, it seems very easy to imagine setups of that form, a Hamiltonian pushing around a vector in Hilbert space, that don't look anything like our world, right? And maybe it seems like a little weird that our world comes out of it in some way. Like, our world is sort of particular in a whole bunch of ways, which is a way of saying, in other words, that the Hamiltonian, if you like, has a whole bunch of special features that get reflected in the features that you mentioned, the symmetries, the locality, space is a really important feature and stuff like that. So maybe features like that, locality and symmetries and charge conservation and stuff like that, maybe those are baked in to the laws of physics by some principles, or maybe God made them that way, or maybe, in other words, there is something special that makes our laws of physics that way. That's one very open possibility. The other open possibility is that it all emerges, right? That the real theory of everything is kind of a chaotic jumble, but Everett allows branches of the universe to come into existence, and these branches come into existence, and on each different branch, things look sensible in one way or another. I don't know. I mean, this is why it's so much fun, because like, these are not hard questions to ask, but we have no idea what the answers are right now.
So I guess to just quickly follow up on this idea about why does it look like this in a way, right? I think, so to sort of push a philosophical question, you might imagine that even after you have identified a certain mathematical structure, which has, formally speaking, the properties of space or space-time, there might be the question of whether it is space. So the example that I like to think about is that if we take a square piece of paper that's of area 1, and if we consider subregions of that area, then mathematically those subregions will satisfy the axioms of probability theory. But it would be silly to say that those are probabilities, at least without further theoretical or conceptual baggage in a way. So I'm wondering if there's this kind of an objection that's lingering in the background, where we have to also ask why certain mathematical structures are not just have the right structure, but also are actually able to play the role of space or time.
So I think that I'm not very sympathetic to those kinds of worries, and I'm not sure that I can give you a counter argument other than, yeah, it doesn't seem to bother me that much. Like, I think that if I find a formal structure that exactly maps onto reality, there's some isomorphism between this formal structure and reality, I'm just going to declare victory. I'm going to say, like, yeah, I got it now. If someone says, yes, but your mathematics is not really what it is, I'm going to say, like, what does that mean? What it seems to be a relic, once again, of some old-fashioned way of thinking that there's some pre-existing essence of space or time or whatever that needs to be preserved in the fundamental theory. And I guess my philosophical inclination is just very counter to that. I want to, whenever there is a lurking essence that people want to preserve, I instantly want to get rid of it and say, like, yeah, that's probably something that was convenient when you didn't know any better, but we can do better now. So I'm just not worried about that particular issue. And I know that other people are, and I might be wrong about that, but that's my attitude.
Great. Okay, so maybe it's good to get into some more detailed arguments and results in the space. So perhaps one set of approaches that you talk about is that gets called entropic gravity. So can you perhaps briefly sketch the argument or the main conceptual idea behind entropic gravity?
Yeah, I mean, there's a pre-existing, very, very interesting concept in statistical mechanics called an entropic force. So if you think about, the usual paradigm of a force that we have in Newtonian mechanics might be an object on a spring. So there's like a frictionless surface, a box with a weight, with some mass, a spring connecting it to a wall, okay? And what you very naturally expect is that there's some equilibrium position where the spring is neither pulling nor pushing the box. And if you pull it away, then the spring wants to get shorter. And if you push it toward it, the spring wants to expand. So there's a force that wants to put the box right there, okay? That's the paradigm that we understand. But so now imagine instead of that spring, imagine you have like a very, very lightweight chain. Okay, so you have a chain of links going from the wall to the box. And if the box is closer to the wall than the length of the chain would just sit on the floor and nothing would happen. There's no force whatsoever, right? But now put the whole thing in a heat bath. So imagine you just heat up the room so that the chain starts bouncing around, okay? And so the chain can do many, many different things. And guess what? As soon as you say something can do many, many different things, the idea of entropy comes into the game. Well, how many things can it do, right? How many ways are there for the chain to be one way or the other? And you can convince yourself pretty easily that if you stretched out the chain all the way, so the box, the chain was perfectly straight and the box was as far away as you could get, there are very few ways to have the chain in that configuration. There's only one, right? It's perfectly straight. Whereas if you put the box right up against the wall, there's also relatively few ways to do that. There's a few, because you can sort of smush the chain in a few different ways, but still a small number. And there's some intermediate length distance between the wall and the box where the chain has the biggest number of ways that it could be hopping around at a fixed temperature. So there's effectively a force. Not because the chain is literally pulling, although it is, but it's not because it's a spring. It's just because there are more ways for the chain to be at that favorite length than at any other length. So if the chain is sort of randomly pulling the box back and forth, it will tend to settle into that equilibrium configuration. So for all intents and purposes, there's a force acting on the box that wants to put it at an equilibrium configuration, just as with the spring. But it's an entropic force, not a mechanical force. If that distinction is clear. So people like Ted Jacobson and Eric Verlinde and others have suggested that gravity could be thought of as an entropic force. In other words, rather than just saying what really exists is space-time, and it curves in a certain way and pushes you around, that's what Einstein would say. That's the mechanical version of gravity. You say that there are some microscopic degrees of freedom. Don't ask me what they are. We don't know what they are, okay? But there's many of them. And what you think of as a force pulling two objects together, the force due to gravity, is really just the microscopic degrees of freedom that make up space-time itself, trying to arrange themselves into the highest entropy configuration they can be in, given the macroscopic constraints of the objects and stuff like that. It turns out this is, I think it's fair to say this is still quite preliminary, ill-formed. We don't yet have a fully rigorous working out of what's going on, but it seems to be possible to recover the standard classical results of general relativity starting from a set of assumptions like this. So Jacobson's first paper was actually called the Einstein equation of state. So he's making a little joke because equation of state is what in a gas would relate the pressure and the density. So you have a gas in a piston, you push the piston, and you say, how much does it push me back? And it has to do with how many molecules you have and stuff like that. What Einstein really has is Einstein's equation. And what Jacobson is saying is that you can replace that mechanical equation with an equation of state that represents the statistical properties of some as yet unspecified microscopic degrees of freedom underlying the whole thing.
And this is an idea that gets at least some sort of support from black hole physics, right? Because I think in the case of black holes, people have grown very comfortable thinking about what look like geometrical properties of Einstein gravity, such as the volume, the area of the black hole, as really representing the entropy of some microphysical degrees of freedom that we don't know what they are, but we have good reason to believe that they are, in fact, they're sort of sourcing this entropy.
Yeah, I think that's right, but we should just make it clear that all of this is a little bit speculative, right? So none of it is perfectly well established. It was way back in the 70s when Hawking, following Bekenstein, argued that black holes have entropy, which was already kind of a shock because that meant they evaporate and things like that. But that is stuff that we now accept is probably true. So entropy famously is subject to many incompatible interpretations, right? Many different ways of thinking about what it is. There's information theoretic versions, thermodynamic versions, statistical mechanic versions, etc. And so just because Hawking says, well, black holes have an entropy, it helps relate them to their temperature and energy and so forth, the question of what that entropy really represents is not answered by that particular theory. So you're right, most people now think that the entropy of a black hole should be thought of just like the entropy of a box of gas. It's representing the collective behavior of many, many microscopic degrees of freedom. Now, there's another sub-question there, which is there is a quantum mechanical version of entropy called the entanglement entropy. When you have two systems like Schrodinger's cat and the air around it, I tried to, it went quickly by, but I said, you can't talk about the cat as having a wave function all by itself because it's entangled. So just like with a box of gas, entropy arises because you don't know where each individual molecule is, right? You have some probability distribution. When one quantum system is entangled with some other quantum system, there's a sense in which, this is an idea worked out by John von Neumann in the 1930s, a brilliant mathematician and quantum physicist. He noted there's a formal similarity where if a system that you care about is entangled with the outside world, there's a sense in which the system has a state, but you just don't know what it is. Just like with the classical box of gas. Like with the classical box of gas, there is some position and momentum for all those particles, but you don't know what it is. So instead, you speak a language of entropy and density and things like that. So von Neumann says, there is a state of the whole universe, but if I ask just about the state of the cat, for example, I don't know what that is. So I can assign an entropy to the cat based on how entangled it is with the rest of the world. So that's called entanglement entropy or von Neumann entropy or quantum entropy. So with Hawking's black hole entropy, it would be very natural to imagine that the entropy of black holes represent the entanglement of those microscopic degrees of freedom with the outside world. So I would say that, almost everybody in their right mind thinks that black holes have entropy. Not everyone does, but almost everyone does. Most people think that entropy can be thought of with some microscopic description that we just don't know what it is yet. And probably most people, but still a subset, think that you can think of that particular microscopic entropy as arising from entanglement with the outside world.
Right. And the idea with respect to the entropic gravity program is that it's not just the geometrical properties of black holes, but the geometrical properties of all of space-time that comes through as a kind of entanglement entropy.
That's right. So Jacobson's original idea was, look, if you tell me that a black hole has an entropy, in particular, what Hawking said is that the entropy of a black hole is just the area of it, the event horizon of the black hole, measured in Planck units. So Planck length squared is a little Planck area, and the Planck length is the tiny quantum gravitational unit of distance. So there's a formula that depends on the area of the black hole, and that gives us the entropy. The entropy is in fact the area divided by 4 in the correct units. So Jacobson took a leap and said, well, maybe that's not just black holes. Maybe this relationship between entropy and area is more general. And in particular, he said, if I have some region of space-time and I draw like a boundary around it, okay, and I say, well, that has some entropy. Sadly, in most conventional calculations, that entropy is infinite. This is one of the technical difficulties in doing quantum field theory or quantum gravity, but ignore that. Ignore the fact that it's infinite. Just say it's some number. And he said, now imagine putting some matter or energy in that region, okay? So now that matter and energy has gravity. It affects the geometry of the space around it. It affects the area of that boundary that we drew. And he says, I'm just gonna posit that there's a change in entropy proportional to that change in area. There's a bunch of mathematical complications that go into this, but this was his assumption. And so the fact that the original entropy was infinite doesn't matter. It was some number and it changed. Its change is finite. Okay, that's what he was positing. And from that assumption, he's able to derive Einstein's equation for general relativity in general, not just for black holes. So that was a very impressive feat that made people think that there's something behind this.
And in one of your papers, which you co-authored with Grant Remen, you make a distinction between two approaches to entropic gravity, namely holographic gravity and thermodynamic gravity. Could you briefly just elaborate on this distinction?
Well, so Ted Jacobson, who I keep mentioning, who is the pioneer here, he's a friend of mine, and Grant, who is a student of mine now, he was a student at Caltech. Now he is a postdoc, I think, still at Berkeley, but he might have gone on by now. I'm older than I used to be. Like, my students are now doing things. So we had this idea, like, Ted had written this paper in 1995, the Einstein equation of state, a brilliant, very influential paper, where he defines a bunch of things, and we just couldn't quite make it work. Like, we couldn't, attach meaning to the words that he was using in a way that made us happy. But for better or for worse, like, while we were thinking about that, we were going to write a paper saying, we don't understand how this works. Ted wrote another paper saying, like, here is a new version of my old idea. So this is like 20 years later. And we looked at that paper and it seemed exactly right. Like, okay, this one actually works. And the difference was, in the original paper, it was thermodynamic. I think I'm getting the nomenclature right. Like, this was a few years ago that I wrote this paper. The original version was, it's kind of hard to describe, but it was more or less what I just said. It was more or less like you had this region of space, you add some matter to it, the area changes, etc. And it was kind of phenomenological. Like, it was really, there was no microscopic physics at all. There was just this posit of entropy being proportional to area. In the new paper, he does something a little bit more sophisticated. He has there's what's called a causal diamond. So if you imagine in your mind a space-time diagram, and some people in the audience might be very happy with this and some people might not, but the point of a space-time diagram is space is this way, time is this way, and if you start at a point and send out light, it goes in a cone, right? It goes in all directions at 45 degrees. So if you imagine a little trajectory in space-time of not light, of a person or something like that, from one point aging a little bit in time to this point, there's sort of the future light cone of the starting point and the past going light cone of the ending point, and together they make a little diamond in space-time. And this diamond in space-time is the set of all the points that both can be influenced by and can influence that little person on their trajectory. So we call that the causal diamond. And it's an interesting idea because, causality is important to philosophers, but in a slightly different sense. But, it's interesting to connect those ideas. So Jacobson says, like, all I'm going to assume is that if I make a really tiny little causal diamond, then very much like Einstein assumed when he invented general relativity, I'm going to say it's basically flat space-time, right? Like, if I'm in a small enough region, then the fact that space-time is curved and warped becomes less and less important. That's just the principal equivalence, right? That's just Einstein's elevator once again. And then he uses some quantum field theory, and you can actually do, and I can't go into the details, sorry about that, but there's some quantum field theoretic calculations where you can basically define how entropy can not just be posited, but can be derived in the limit of a sufficiently tiny region of space-time. And what, sort of, there's something called the modular Hamiltonian, which says, a way of measuring energy if all you know is the quantum state, not the real Hamiltonian of the system. And you can calculate the entropy based on that. Anyway, I think that probably what I just said is of no use to anybody, but I'm just letting you know that he invented what we think is a more sophisticated way of deriving the same thing and getting the same answer. So Ted still thinks that his original idea works perfectly well, and we tried to make the argument that we were skeptical about the original idea, but the latter idea works perfectly well, and we actually sort of suggested some ways to actually argue in favor of some of the assumptions that he made. So I started out as a little bit of an entropic gravity skeptic, but this sort of more modern holographic version, I think, is definitely on the right track. And later on, I used it with other collaborators in other contexts.
Well, it's kind of interesting because these kinds of approaches allow you to get a handle on what the underlying microphysical degrees of freedom, if there are such things giving rise to our gravity, what they might be or what they might be like without really knowing very much about it, right? It's kind of cool that you can sort of work backwards a little bit and figure out some features.
Yeah, no, I think that's exactly right. I mean, the reason why it's hard is because we can't do direct experiments that are relevant to quantum gravity, right? We can't build a graviton collider. What we have is the basic rules of quantum mechanics and the basic rules of gravity, right? And our brains. And so that makes it very, very hard. But, again, no rose gardens were promised, and we need to sort of think about whether we can make progress. And by the way, there's no guarantee we can make progress. Like, maybe we use our brains all we can, and still the problem is just too hard. And 1,000 years from now, we still know how to quantize gravity. There's no guarantee. But we haven't done all the work that we can possibly do. So I do think that it's interesting that we can make this progress, like you just said, without having the complete theory. So like there's an approach which is what string theorist or loop quantum gravity person would do, which is to say, let me just guess the right theory and then try to work out what the implications of that are. What we're doing is much more, in a sense, phenomenological. In a sense, that's why I call it reverse engineering. We know what gravity is supposed to be like. We know what the basic features of quantum mechanics are like. How much progress can we make just trying to put those together into a consistent framework?
Along the same lines, another interesting paper that you have written with Ning Bao and Ashmeet Singh is that you've argued that if the Hilbert space, so we talked about Hilbert space a little bit and about the dimension of this Hilbert space, which might be infinite, but you've argued that the dimension of some finite patch of space, the Hilbert space dimension giving rise to some finite patch of space, might be actually finite. And you give an argument about this, even though we don't know anything really about that underlying quantum mechanical physics. So can you perhaps just give us a sense of how we might be able to figure out something like that?
Yeah, I mean, we wrote this little paper. It's actually an essay. There's a yearly essay competition in Gravity, the Gravitational Research Foundation, Gravity Research Foundation essay competition. So it's an excuse, and in fact, Ted Jacobson's original paper was the winner of that competition back in 1995. It's a good competition because it gives people an excuse to let their hair down a little bit. Like, rather than saying I have a dramatic new result that I would like to get published, people get to say like, well, what about this? Like let's consider the following idea. And what we were doing was basically taking this idea that degrees of freedom, that there's only a finite number of degrees of freedom in a finite sized region of space, which a lot of people sort of casually thought was true, right? And we tried to like sit down and make sense of it, a little bit. So it wasn't a dramatic new result, but it's like, what are the pros and cons of this idea? And the reason why the idea makes sense is because two reasons. Well, one reason, black hole entropy is the reason. Bekenstein back in the 70s and then followed up by Hawking, not only did he say that black holes have entropy, but there's a number, and it's a finite number. And so if you think, as we said before, if you think that entropy can be thought of as entanglement entropy between what's inside the black hole and what's outside. Remember I said that in regular old field theory, this is the problem that Jacobson sort of got to slide around, a region of space is entangled with the outside world and therefore has entropy, but it's infinite, right? So that's an obvious problem if you think that you want to make the gravity of a black hole be entanglement entropy, because the entropy of just any region of space is already infinite. So how in the world could the entropy of a black hole be a finite number, right? Well, the answer would be that the entropy of a region of space really isn't infinite. It's because quantum field theory is wrong. Because quantum field theory, which says that, you know, there's these fields filling space and then we quantize them, it's a good approximation at low energies and large distances. But according to that approximation, in this region of space, I could put an arbitrarily large amount of energy, right? I could make my quantum fields vibrate as much as I want. So in this region of space, I could have any energy I wanted. What Bekenstein pointed out was, look, you might think you can do that, but once you get enough energy, it's going to make a black hole. And then once you make a black hole, you cannot fit any more energy into that region of space because the black hole becomes bigger than that region. The area gets bigger as the more mass and energy are put in the black hole. So there's an upper limit on how much stuff you can possibly put in any one region of space. So quantum field theory is not the entire story. And if you say, well, the actual upper limit of what I can do in that region of space is given to me by the entropy of the black hole, that's a finite number. And the quantum mechanical version of that is there's only a finite number of quantum mechanical degrees of freedom in that space. And that means there's a finite dimensional Hilbert space. So the interest of it to me is, like, unlike everybody else, I'm coming at it from this point of view where we should start with quantum mechanics and start with Hilbert space and start with wave functions. And the very first question you could ask is, what is the dimensionality of your Hilbert space? How big is it? And the very first sub-question is it finite or infinite, right? Like we said that the simple theory of one electron in a non-relativistic electron in otherwise empty space has an infinite dimensional Hilbert space. So the dimensionality of Hilbert space has nothing to do with how complicated the theory is. But we would like to know the answer to that. So, you know, yeah, Ning and Charles and I sort of leaned in on this, sorry, Ning and Ashmeet and I for that paper, you know, honed in on this, you know, can we make sense of the idea that there are only a finite number of quantum mechanical degrees of freedom in any one region of space-time? And we argued yes.
So the idea is that you can't really pack energy in denser than black holes. And,
exactly. So there's some, gravity gives you a cutoff. Gravity tells you there's only so many things you can do in a finite sized region of space.
And given that we already have a handle on black hole entropy, we can sort of make a guess about what the
we can actually figure out how many things there are. Yeah, that's right. It's not just there's a finite number. We know how many there are.
So it's kind of really the Hawking's and Bekenstein's calculations about black hole entropy are really foundational in this whole approach, in a way that they're one of the most important handles we have, right?
Yeah, absolutely. You know, I mean, it's a weird thing that Hawking did. He gave us a puzzle. Like, it's not the end of the story, black hole entropy. It's the beginning of the story that we're nowhere near completing yet. And so that's a pretty good legacy to leave theoretical physics. Like, so much of modern theoretical physics is thinking about black hole entropy in one way or another. It's kind of amazing.
To the viewers out there, I did an interview with David Wallace on black holes and black hole entropy and all of that. So if you're interested in exploring this topic more, I recommend that interview. So I think we are coming up close to the end of the time, but perhaps I can get in a couple of more philosophical questions and see what you think. Mm-hmm. So in philosophy, there has been this long-standing debate between relationalists and substantivalists about space and space-time. So relationalists believe that all the properties of space that we think space has, they can all be reduced in some kind of final analysis to the relations between material entities. And the substantivalists, on the other hand, think that space has properties that cannot just be reduced to relations between material entities. So perhaps one example is that if we think about perhaps friendship as a relation, there's nothing more to friendship other than the relations between human beings, right? But you can think about this this Zoom call, which is inducing a relation between you and me, but it has many more other properties that it has. So, so the thought that I'm having is perhaps can you view this quantum space-time project as a kind of relationalist project? That is, you're trying to say that space-time is nothing over and above the relations that it induces between certain quantum mechanical degrees of freedom?
In some sense, yes. You know, I want to, I'm not sure that this particular dichotomy is relevant or is the best way of thinking about what's going on. For one thing, I think space-time is overrated, right? I mean, I think that people in both physics and philosophy spend too much time thinking about the details of how space-time works when we know that at best it's an approximation, right? It's not, you know, the world's not classical. Einstein was not the final story about the nature of space and time. It's emergent, it's a higher level thing. So don't press it too hard in some sense. But, you know, I do want to be, I tend to be more, I guess, relational, but I want to say operational. You know, I'm like, well, what do I use it for? This idea, and you know, part of our idea about emergent space is that we can reverse engineer things like distances and areas from quantum mechanical properties like entanglement and entropy. So certainly, I wouldn't want to say that those geometric properties are more fundamental. I don't think that they are. On the other hand, when you say relations, then you know people are going to say, well, between what? And you sort of sneaked in there material entities, but I don't know what that means. And maybe you can say quantum mechanical degrees of freedom, but it's not even that easy, because this is, you know, goes back to what I said a while ago about how I don't want to think of these emergence relations as literal physical reductionist relations. Like the pieces out of which we make the microscopic theory are not necessarily literally smaller. And that's an absolute lesson both of quantum mechanics and of holography in quantum gravity. So there is a theory of quantum gravity, and there is a map from that theory to a classical theory that is valid under certain regimes, right? That's the kind of thing I'm going to allow myself to do, but it's not that sort of strictly reductionist idea that I can take a big system and divide it into small subsystems, and the collective behavior gives rise to the big one.
Yeah, I think in the philosophy of reduction and emergence, there has long been a recognition that mereological reduction, that is reduction of a large into reduction of its parts, is just one kind of reduction that you could do, and that in general, reduction tends to be a lot more complicated, and usually you can't just look at things that compose it sort of spatially and then say that these are the things that it reduces to. Even very simple phenomena like waves in water, you might have to think about large scale, the relations that it has to its outside environment and patterns. Actually, that's not a very good example, but I'm blanking on good examples right now, but there are good examples, which.
Well, I think quantum mechanics is the best example. You know, I think that quantum mechanics is non-local in a very straightforward sense, and nevertheless, the sort of local classical reality emerges from it. And so, you know, the wave function of an electron is not made of little wave functions. That's just a bad idea.
A small point that might bother some people is that if we are thinking of space-time as emergent, and we are saying that it is coming from this wave function, and earlier you mentioned the Schrodinger equation, and one might imagine, okay, so what is this evolving with respect to, right? I mean, if time itself is supposed to come out, what is the coordinate with respect to which we are saying it's evolving? Because it can't be time, because otherwise we are back to the old putting it in by hand approaches.
Well, I think this goes back to the fact that we know so little about the very, very basic, easy questions. I don't know whether time is emergent or not. So I never said that time is emergent. Space-time might be emergent, even though time is fundamental. You know, there might be different ways of slicing up space-time, but they're all equivalent. Space and time in these quantum theories, these emergent space-time theories, space and time are not on an equal footing a priori in the way that they are in relativity. So that might be because we don't have the final formulation of these theories, or it might just be because Lorentz invariance, which sort of dissolves the difference between space and time, is only an approximation itself. In fact, that's probably the most promising route for an experimental test of these ideas. If we ever get that far, we don't have it yet, but it's plausible that what we what we predict using these formulas, using this approach, is that some old, very precious ideas like Lorentz invariance are just approximately true, and maybe we can experimentally look for deviations from them. So I think it's entirely possible that time is fundamental, that it's right there in the equation. I mean, it's right there in the Schrodinger equation as a variable, d by dt. On the other hand, I also think that it's entirely possible that it's not fundamental. I think we just don't know. And if it's not fundamental, then it will be something like relational. In other words, in the wave function of the universe, the way that it will work is there will be superpositions of, here's my system doing something, and here's another system which acts as a clock. And they're entangled. And they're entangled in such a way that if I observe the system, then I know what the clock is reading, or vice versa. So the answer to the question, with respect to what does the system evolve, it's to this other subsystem, which is acting like a clock. But again, I don't know if that's actually true or not.
Right. Yeah. I guess the idea, and I think people have tried to catch something like this out even before we get to quantum gravity, is that what we think of time is that it's kind of silly to ask how fast does time go, because the answer is just going to be
right
1 second per second or something like that, right? So the only thing we can say is that this little bit of matter changes in a certain way with respect to that little bit of matter, and and the suggestion is that perhaps the time in our space-time is also something like this, but here the relations are much subtler, or actually we really don't know much about it.
Yeah, no, I think that's right. So people there's a certain segment of people who seem to have the impression that we know that time is not fundamental. And I just don't think that we know that yet. I think it's okay to admit that we don't know yet. Maybe we don't. Maybe it's not. But let's just keep plugging forward on both possibilities until we get one that really works.
Another kind of philosophical question that might come up is that, so you were very careful to emphasize several times that we are not supposed to think of this kind of reduction as reduction of some larger entity to little bits that compose it. And in philosophy, at least in metaphysics, there's this view which has been resuscitated somewhat by Jonathan Schaeffer at Rutgers, which gets called monism. And on this sort of view, what is fundamental is really what he calls the cosmos, or the whole. And basically everything else, like things that we right now think as being more fundamental, that is things like quantum fields, are really sort of emergent from the more the bigger whole. Do you kind of see some affinity with this kind of view?
I think so. You know, I'm not very familiar with it, but people do always, want to say, like, what are the strings really in string theory? Or if you're saying that space-time arises from entanglement between the degrees of freedom, quantum degrees of freedom, what are these quantum degrees of freedom really? And these questions have to bottom out somewhere. And I do eventually end up saying, well, that's what is. There it is. So there is. I'm very sympathetic to the idea there is something that is real, the world, the cosmos, reality, whatever you want to call it. And what we're doing is looking for models of it. So far, we have models of it in sub-regions of possibility space. What we're looking for is a model that works in all regions of possibility space. May or may not be able to ever achieve that, but that would be nice. But yeah, I mean, in some level, even if, but I guess what I hesitate about is this. What if the world were just like Tinker Toys? Like, what if it really were literally made of little things tied together in big things? It would still be possible to say that the big thing is what exists. And the little things are a convenient way of dividing it up. So I'm not quite sure how much oomph there is to saying that the cosmos or whatever it is the only thing that exists. I mean, that there's a cheap sense in which that's always possible to say. Maybe there's a more a sense that has more bite to it than that, and maybe I'd be sympathetic to that, but I'm not quite sure what it is.
Okay, so the final question then, and you have basically answered this question in some way or the other throughout our conversation, but perhaps it would be nice to sort of tie it up in a nice bow. So what are some research directions or questions along these topics that you think are underexplored relative to their interestingness or importance?
Yeah, I mean, I think that there are a lot, like I have mentioned a bunch of times already. You know, I think that when you go to conferences on the foundations of quantum mechanics, it's a little bit weird because people don't agree on the foundations of quantum mechanics. So you have, you know, Bohmians and collapse people and Everettians and epistemic people trying to talk to each other and doing a sort of a half-hearted job. And, you know, my personal state of belief is that I think that my credence in Everettian quantum mechanics is large enough that what I want to spend time doing is developing that theory rather than comparing it to other theories. And I think that there's an enormous amount of work to be done there. I mean, people like David Wallace, among others, have done an enormous amount of work already, but it's just not that hard to think of questions we don't know the answer to yet. Why is there space-time? What kind of Hamiltonians give rise to something called space-time? What is the quantum mechanical version of the past hypothesis that says the early universe had low entropy? What are the implications of the dimensionality of Hilbert space being finite versus infinite? Does time have to emerge, or can it be fundamental? You know, like, all of these questions are right there. How do you divide up the wave function into subsystems? The mereology question, which we mentioned and I've been just writing about. Can Lorentz invariants or other symmetries be approximate? How would you notice this? You know, just a million sort of very basic questions lying right there waiting to be picked up. And it's a little bit, you know, to be fair, physicists, or not to be fair, but to be honest, physicists aren't necessarily interested in these questions. I mean, they think that they know more than well enough what the answers are. So there are much more down-to-earth questions about, you know, how do you build a quantum circuit to do a certain kind of thing? You know, how do you squeeze most information out of a quantum state? How do you invent a quantum code that will correct errors that might be made along the way? And these relate directly to questions in quantum gravity. Like, one of the hot research topics these days is how to relate the conformal field theory side of ADS-CFT to the ADS side using ideas from quantum information theory, like quantum error correcting codes, okay? Tensor networks and quantum circuits and things like that, thinking of space-time itself as a quantum circuit. So I mentioned those questions because there's a bunch of physicists who are very successful who agree that those are good questions. And these other questions I mentioned, I think are good questions, but it's a more minority view in the physics community.
Yeah, I think in physics, there's this strong preference to make a certain kind of calculational progress, at least, right? Like, you want some very definite quantity calculated. And it's not as if that the questions that you suggest can't have those kinds of precise calculational answers. It's just that it's a priori hard to figure out what the right calculations to do are.
Exactly. Yeah, that's right. I mean, there's a reason why, you know, there's the number of papers written about anti-de Sitter space by fundamental physicists in the last 25 years is way bigger than the numbers written about de Sitter space, even though the world we live in is much closer to de Sitter space, so the one with a positive vacuum energy, because the calculations are much more well-defined in the anti-de Sitter case. So there's a matter of taste that comes in to how people decide to spend their research time. Like, do you want a well-defined problem, or do you want one that is more obviously relevant to the real world? And, you know, it's not a right or wrong answer. They're both important, and it's not clear. You know, at some level, we're all guessing as to what route is going to get us to the answer in the most direct way. And it's good that people have different guesses about that. That maximizes the chances that someone will be on the right track.
Sean, Carroll, thank you very much.
Thank you very much, Siddharth. It was a great, fun conversation.